Hello, I'm Rebecca Barnes and welcome to the Science ESA vodcast. In this episode, we will identify some of the key discoveries achieved with the famous Hubble Space Telescope, look at the concept of redshift, and meet a new telescope that we used to uncover the early universe. The Hubble Space Telescope is one of the most successful astronomical space telescopes of all time. Its impact has been far-reaching and profound. Launched in 1990, the NASA ESA Hubble Space Telescope has provided astronomers with the deepest and clearest views of nearly all types of astronomical objects. Stunning Hubble images now provide a familiar view of the cosmos in visible, ultraviolet and near-infrared wavelengths. It is possible to view the visible universe from Earth. Hubble, however, has the vantage point of an orbit above the blurring turbulence of the Earth's upper atmosphere. Images from Hubble may indeed be beautiful, but these observations have also provided astronomers with key information about the universe.
In the last 10 or so years, more than 300 planets have been discovered orbiting stars other than the Sun. Hubble made the first measurement of the chemical makeup of the atmospheres of these exoplanets, detecting elements such as carbon, hydrogen, and oxygen in the atmosphere of a Jupiter-sized planet. After the Big Bang, the expansion of the universe started to slow down. However, when the universe was less than half its current age, it started to expand at an increasing rate. It was discovered that a mysterious repulsive force, known as dark energy, is the cause for this acceleration, working in opposition to gravity. The Hubble Space Telescope played a key role in this discovery by providing high-precision measurements of the brightness of ancient and therefore distant supernovae. This image is known as the Hubble Ultra Deep Field. It is the deepest view ever achieved of the visible ultraviolet and infrared universe. The image contains about 10,000 galaxies in an area of sky that is just 1/10 of the diameter of the full moon. Some of these galaxies are the oldest ever seen and existed just 400 million years after the Big Bang. Cepheid variables are a group of stars that change in brightness in a regular and therefore predictable way. This makes them extremely useful to measure vast distances in space. Hubble observations of Cepheid variables helped astronomers to determine the age of the universe. They found it to be between 13 and 14 billion years old, with an accuracy of about 10%. Cepheid variables are also used to determine the expansion rate of the universe.
The celebrated Hubble Space Telescope detects the visible light emitted from mature, fully formed stars and galaxies. To further investigate stars and galaxies of the early universe, astronomers need to study the ultraviolet and visible light emitted at this time. By the time this light reaches our solar system, it has been stretched or redshifted into infrared wavelengths during its vast journey across space and time. We're all familiar with the physical phenomenon known as the Doppler effect, which occurs when a source emitting sound or light waves is moving with respect to an observer. This is something that can clearly be heard when a siren or a fast train moves past. As the sound source moves towards us, the pitch gets higher, and then lower as the sound source moves away. Redshift is the astronomical version of the Doppler effect. In redshift, the peaks of electromagnetic waves are detected closer together as a source is moving towards us, which means that the light is shifted towards the blue portion of the spectrum. If a source is moving away from us, the wave peaks are more stretched out, and hence the light is shifted towards the red portion of the electromagnetic spectrum. In the 1920s, Edwin Hubble discovered that the velocity of a galaxy moving away from us is directly proportional to its distance. This is known as Hubble's law. The faintest, most distant galaxies are moving away from us with a greater velocity, and therefore exhibit a larger redshift. Most galaxies have been observed to be moving away from us. However, redshift is not due to the waves themselves stretching, it is due to the expansion of the universe. Electromagnetic waves are carried on the fabric of space, and because this is expanding, the waves appear to be stretched. Redshifts are measured from the signature absorption and emission lines of atoms and molecules that are present in the spectrum of celestial objects. The wavelengths of these signature lines can be measured very accurately and are known. They can therefore be compared to the spectrum of a galaxy to calculate the redshift. If signature absorption and emission lines of a galaxy's spectrum have shifted to wavelengths that are twice as long, the galaxy has a redshift of 1. If the signature lines have shifted to wavelengths that are 3 times as long, the galaxy has a redshift of 2. The Hubble Deep Field Survey exposed faint and distant galaxies with redshifts up to about 6. To view galaxies at even higher redshifts, in other words, to go back to the earliest galaxies, then astronomers need a telescope that is extremely sensitive at near and mid-infrared wavelengths. Since 1996, NASA, ESA, and the Canadian Space Agency have cooperated on designing and constructing a worthy successor to the Hubble Space Telescope.
The JWST Space Telescope is due to launch early in the next decade. This mission will look back to the very furthest reaches of space to see galaxies that have a redshift of 15 or more, where the visible ultraviolet light they emitted has now shifted to near and mid-infrared wavelengths. Sometimes known as successor to Hubble, there are many aspects of JWST telescope that are very different, such as the wavelengths of the light it will detect, its orbit, and its size. All objects, including telescopes, emit infrared light, which makes the faint infrared light from the distant early universe difficult to detect. This light could easily be swamped by brighter and closer infrared sources, such as the Sun, Earth, and Moon. Therefore, the JWST Space Telescope's 4 scientific instruments will be protected from these objects by a tennis court-sized sunshade, as well as being placed at the second Lagrange point, L2, an orbit where the Sun, Earth, and Moon will be in the same direction at all times. When it's launched, the JWST Space Telescope will be the largest space telescope ever flown, with a primary mirror that is 6.5 meters in diameter. In fact, this space telescope mirror is the first to have a diameter that is larger than that of the launcher fairing, and it will have to be folded to fit into the ESA Ariane 5 ECA launcher. Designing and building a mirror of this scale that will unfold is one of the major technological developments of this mission and has never been achieved in space before. During its journey of 1.5 million kilometers to L2, the JWST Space Telescope will be fully deployed. Once the communication antenna and solar arrays have unfolded, the giant sun shield will open out, exposing the folded mirror. The sun shield is made of a polymer-based film and will have to be covered for the launch. Designed to block out sunlight and to keep the entire telescope operating at 33 Kelvin, the sun shield is multi-layered. Once it has been fully opened, it will then separate into 5 layers. The large primary mirror is made up of 18 hexagonal segments that will also unfold and move into position en route to L2. The JWST Space Telescope mirror is designed to resolve the faintest detail possible for its size when observing near-infrared wavelength. The hexagonal segments of the mirror will be movable to allow for fine-tuning of the images in orbit. With this huge mirror and cold instruments, the JWST Space Telescope will be equipped to detect highly redshifted light emitted from the earliest galaxies.
Hubble provided a glimpse into the distant past that has driven the development of James Webb. This new space telescope will provide a better view of the very distant galaxies revealed by Hubble.
The James Webb Space Telescope will detect the redshifted light from the very first stars that formed. When these formed, they ended the cosmic dark ages. This period followed the emission of the first light after the Big Bang, which is now detected as the cosmic microwave background. Little is known about the nature of these first stars or exactly when they were formed. This mission will also conduct ultra-deep infrared surveys of the universe in search of the very first galaxies. This will help astronomers to tackle some of the fundamental questions about galaxy evolution, such as, how did the first galaxies form? How did we end up with the large variety of galaxies we see today? And what is the nature of the relationship between the large black holes at the centers of many galaxies and the galaxy that hosts them? The processes by which stars and planets are made are also poorly understood. Using the near-infrared portion of the spectrum, the James Webb Space Telescope will be able to infiltrate the dusty shrouds around newly born stars to study the young stars themselves. This telescope will also allow astronomers to investigate systems of planets orbiting other stars, watch how they form, and find out what organic molecules they contain. This, along with studies of the cold, icy bodies in the far reaches of our solar system, will help trace the origins of Earth and life in the universe.
In the tradition of the Hubble Space Telescope, astronomers will use its successor, the James Webb Space Telescope, to follow the redshift back to the earliest stars and galaxies. By constantly pushing technology to its limit, they are sure to achieve their goals. I'm Rebecca Barnes. Thank you for watching the Science ESA vodcast.